right, ladies and gentlemen, welcome back to the Are We Cool video notes. This is our 5th video, and we left off part 2. And you can see that I added the splendid Mises because we were supposed to create a new organism to represent this population growth, this J-shaped, remember J-shaped, population growth curve. This shows how the population grows over time. Number 3, it says identify region on graph where population equals 500. So you're supposed to have drawn this graph in your notebook for slide 24, and then you're supposed to identify when the population reached 500. And that's I came up with a little symbol there. Number 4, so in your notebook, make sure you identify where the population reached 500. So you just line it up with the vertical axis, the y-axis. Next, it says identify region on graph where population doubles from 500 to 1,000. I have my little marker up here, and I'm going to put it and balance it with the 1,000. So this is where the population reached 500, and then quickly thereafter you see that it reaches 1,000. So it took this long to reach 500, and even a shorter period of time to reach 1,000. That's exponential growth. When a species over time grows faster and faster over less time, that's exponential growth. All right, so we want to finish this slide. So for slide 24, let's answer question 5 now. It says explain how amount of time was different for the population to reach 500 versus how long it took to reach 1,000. So if you see the time is here. This is how long time took to reach 500. And look at this little arrow here. This little arrow is how much time it took for the population to go from 500 to 1,000. Originally, to go from 1 to 500, it took this long. But to make the same amount, to double or go twice as much, it only took this amount to go from 500 to 1,000. That's called exponential, because the population is growing faster than it used to. This long to do 500, this long to double it, to go to 1,000. It's growing quicker. So it said it took a short or long time to reach 500. So we would say it took a short time to reach 500, but it took and you decide, did it take longer or shorter time to double the blank? What are we talking about here? It's a population to 1,000. Finish this sentence as best you think you should, and we'll go over it in class later, all right? All right, you've just completed slide 24. Let's move on. All right, here's a J-shaped population graph for you. This is a bacteria population, and it shows J-shaped growth over 5 hours. So this is the 1st hour, 2nd hour, 3rd hour, 4th hour, and 5th hour. So bacteria grow fast. The 1st hour, there was a population of 800 bacteria. By the 5th hour, there's more than 3 million just after 5 hours. So bacteria can reproduce and make more than 3 million of them in 5 hours. Humans do not do this. Bacteria, very good at reproducing, very good at having sex and making many of themselves. Look at this. In the beginning, within the first 2 hours, in 1 hour, the population increases by 5,500. But look here. At the 5th hour, at this time, the population increases by almost 2.5 million in just 1 hour. In 1 hour, they can increase their population by 2.5 million. But in the beginning, they could only increase their population in 1 hour by 5,500. So you see, as they get older and as time goes by, their population increases faster and faster. And that's why this line gets steeper and steeper. As the line gets steeper, the population grows more and more. That's exponential. All right, here's slide 26. There are some notes to write in slide 26. So, in your notebook, copy down slide 26, and here it is. It says population growth is a J-shaped line and shows exponential growth. This is a J-shaped line. So in your notebook, copy this down, copy what's in the big box, and then copy this graph down so that you can see that it's J-shaped growth. Remember, populations don't have straight line or linear growth. Populations do not grow in a straight line. You don't have a perfect slope like this, a straight line or linear growth. You don't. But you always have a J-shape. So populations, organisms, always grow J-shaped. Just like the bacteria. J-shaped, exponential. Over time, the population grows more and more over time. All right, that's slide 26. It's pretty simple. All right, let's move on. Let's move on to the next slide. Slide 27 is simple. It says, imagine a species that can have 2 babies every year. So if there's a species that can have 2 babies every year, look over after each year. Each one of these is a year, right? First year, second year, third year, fourth year, fifth year, sixth year, seventh year, eighth year. Over time, can you see how fast the population can double or increase? So exponential growth is, after each year, the population grows faster and faster. And that's why the line is so steep. You can see it takes less and less time to double their population. Exponent, exponential, double. All right, here's an interesting activity. So imagine that we have humans now. So we're thinking about people, us. Let's pretend that one couple has 1 kid every year. Most humans, 1 kid each year. This couple stops having kids after the 10th year. So every year for 10 years, they have a child. 1 child every year for 10 years. Listen to this. It says, in 2038, all the children they have can reproduce. So by 2038, all their children will be old enough to have kids of their own. And if each of their kids have kids when they're 16, the question is, how long would it take this family to reach 112 people if their kids had babies as soon as they could every year? Think about this. This is what it would look like. If we started in 2013, you can see it all starts with 1 couple and they have 1 kid. By 2037, you can see it would look just like this. It would be the original couple, plus by 2037, they'd have their 10 kids, and all of their kids are now 16. If by 2046, this population would reach that goal of 112. You can see over time, the population grows faster and faster. Exponential growth. Slide 29. So in your notebook, please write slide 29, and let's write exponential growth. As a population gets larger, it grows faster. Slide 29, and it has the official definition for exponential growth. All right, just think about exponential growth. Think about these populations growing faster and faster over time. Here's a video by National Geographic. I'm just going to let it play. Let's give credit where credit's due. It's a fantastic video. Check it out. So it says by 2011, there was 7 billion people on Earth. Crazy sauce. So humans can grow exponentially too. So in 1800, the world's population was just 1 billion. So it took thousands and thousands and thousands of years for the human population to reproduce and reach 1 billion. You can see it should be kind of a J-shaped curve. It's going to get steeper and steeper. Check it out. This is exponential growth. Look at this. We are now adding 1 billion within a few decades or less. We can add 1 billion to our population so much faster. It takes a decade or 10 years instead of taking a whole, I don't know, thousands of years that it used to take. So by 2045, we could be 9 billion. About every second, 5 people are born. 2 people die every second. By the time this video is over, 160-something people have been added to our population. The world population. Back in the day, in 2010. So life expectancy is increasing. So people are living longer and longer. So fewer people are dying. More people are living in the cities. We have a lot more mega cities where people have more than 10 million. Los Angeles, where we live, would be considered a mega city. Look at that. So by 2050, almost 70% of the United States will be living in the cities. We'll all be living in high density, very close together, population dense areas. We might have more conflicts. So if everybody were clustered together, shoulder to shoulder, you could fit all 7 billion people within the boundaries of Los Angeles. So even though 7 billion is a huge number, you could take everybody on the planet and squish them all together, and they would fit within the LA border. Now that's dense population. So the question is if our population keeps growing, how many is too many? Do we have enough space for everybody? Do we have enough resources for everybody? What happens when a population, whether they're humans here or another species, what happens when there's too big of a population and they all need energy and they all need food and they all need drinking water? What happens when a population grows and grows and grows and we have to keep providing all these important energy and resources, water and food for everyone? What happens? All right, so welcome aboard. This is slide 31, and in slide 31, it deals with these questions. What happens when a population gets too big? Well, let's look. It says, eventually, population growth will stop and reach an amount that is stable. So it says that any species will eventually stop growing and stop growing exponentially when it reaches this thing called carrying capacity. This is the amount of individuals an environment can support. So if any species goes up to the carrying capacity, they don't grow anymore, the population will stop growing because there's just too many. Go ahead and pause the video, and in your notebook, write slide 31 and copy down the definition of carrying capacity right here. All right, our next thing is we want to create this brainstorm web. So make sure you draw this bubble, and it should have 3. And then this center one here is titled carrying capacity. So draw this in your notebook with slide 31. This is our brainstorm web. And I want you to think, what things cause carrying capacity? What variables in nature causes populations to die and stop growing? What causes exponential growth to stop? What? What is it that a population doesn't get that would keep them from growing more? I see this one, no space. Do you see? No space. Do you see this little puddle? Baby frogs are trying to live in here. They have very little space. Not enough space. So, no space, growth will stop. Here's another thing, competition. If you're competing too much, some of you die. Harms the population. Competition, too much of it, causes carrying capacity. You think, though, what's one other thing you could write in this bubble? On your own, think of something that keeps the population from growth and that causes it to stop growing exponentially. All right, good luck. That's slide 31. Let's keep moving. All right, you can see from slide 32, this line is carrying capacity. So as the population grows, eventually it doesn't get enough food, or there's too many predators, or maybe there's climate change, but the population can't grow more. So it's stable, and it just kind of grows up to carrying capacity and then no longer grows. That's carrying capacity. Slide 33, we'll have to pick up on our next video, okay? So slide 33, we'll add some more information about carrying capacity and talk about it, and I'll help you answer all these questions, all right? Take care. Have a good day.